All right, let's consider this two-lens system. Here I have uh, an object. I want to know the position of the final image. Two parts to this, three parts maybe. First of all, I want to find out what is the image distance of the first lens. I know that f1 is equal to positive 30. It's a convex lens. P1 is equal to positive 90 centimeters. That is a real object. And to find Q1, I say 1 over f1, 1 over 30 equals 1 over P1 plus 1 over Q1. I'm going to go and do the common denominator, 3 over 90. I just multiplied that 1 over 30 by 3 over 3. Minus 1 over 90 equals 1 over Q1. It's 2 over 90, so Q1 is equal to 45 centimeters. And now M1 is negative Q1 over P1, negative Q over P. That's negative 45 over P1, which is 90, which is negative 1/2. All right, the next part, now that I know that my image is right about here, it's 45 centimeters to the right of that lens. It's inverted and it's about it is half the size of the object. I know that this distance is 95 minus 45 or 50 centimeters. So while f2 is equal to positive 25, that is a convex lens, p2 is equal to 50 centimeters. It is positive as well. It's a real object. I can find Q2. I have 1 over 25 equals 1 over 50 minus 1 over Q2. I'll go and find that common denominator. 2 over 50 minus 1 over 50 equals 1 over Q2. So Q2 is equal to positive 50 centimeters. Then I can find the magnification. M2 is negative Q2 over P2. That's negative 50 over 50. Excuse me, that should be positive 50. Negative 50 over 50, or negative 1. Then my total magnification is just a product of M1 and M2. That's negative 1/2 times negative 1, which is positive 1/2. So now, drawing this image, I know that it's 50 centimeters to the right of the second lens, so right about here. This is 50 centimeters. It is also, notice, has a magnification of plus 1/2. That means it's upright, or it's the same orientation as the original object, and it's half its size. All right, let's look at this. I have refraction. Here I'm moving from an index that is n equal 1 to n equal 1.3. That is moving from an index that is fast to one that is slower. So if I think about my wavefronts, it slows down right here. That means it's going to bend in this direction. So I want to see that you draw these rays correct, the angles correctly relative to one another. Now, as I move from 1.3 to 1.1, I'm moving from one that is slower to one that is faster. So if I think about my wavefronts, it's going to now move away from the normal. And then as I move from a fast again to a slower medium, from low index to high index, then I find that it moves towards the normal like that. And then moving from slow to fast, it will come out like that. Actually, we'll see that this angle and this angle will be the same. So that's part A. I want to see those rays properly drawn so that the angles are proper relative to one another. And I want to know, what is the angle of refraction after the ray exits from medium number 3. So if you're clever, you could just say, well, it's the same as the entry angle, because I know that n1 sine theta 1 equals n2 sine theta 2 equals n3 sine theta 3. Well, I could also say that n0 sine theta 0 is equal to n1 sine theta 1, or we'll call this n0, and then that's equal to n0 sine theta 0. All right, so I see that then whatever the index of refraction is, that is what my exit angle is going to be. So if I'm moving from an n equal 1 to an n equal 1, then the angle theta would be equal to 60 degrees. Um, you know, you could have done this in a very difficult way. Whereas you could have found this angle and this angle and this angle, but I'm not going to go through the laborious process of that. But you could have done that, and some of you probably did, um, where you would have found what this angle is and then set up n3 sine theta 3 equals n sine theta and then solved that for theta. But that was completely unnecessary because you could have just said, well, it has to be 60 degrees, and that's what I would have preferred to do. Okay. All right. An object is 4 centimeters tall. That's the height of the object and the height of the image. So the magnification is HI over HO, which is 2 over 4, or 1/2. And then I also know that it's upright. So I know that that magnification is positive 1/2. That should tell me something. That should tell me that I have a convex mirror. So that if I have an object here, then my image looks like that. Um, So that's the first answer. And then I want to know, what is the image distance? Is the image to the left or right of the mirror? Well, I know that it's actually to the right of the mirror just because I know what types of mirrors produce what types of images. Um, but I want to know the actual image distance. So I know that 1/2 is equal to negative q over p. I also am given the center of curvature. So I know that the focal length is 40 divided by 2, which is equal to 20, but this is a convex mirror, so this has a negative focal length. Very important step right there, that you know that the focal length is negative. So I can also say that 1 over negative 20 equals 1 over q plus 1 over p. I need to solve this by solving the system of equations. I'm going to first solve this for p. P is equal to negative 2q, and then I can put in that negative 2q. So I have 1 over negative 20 equals 1 over q plus 1 over negative 2q. Then I need to write this so it has a common denominator. It's going to be 2q, 2 minus 1, and then I have negative 2q equals 2 minus 1 equals 20. So q is equal to negative 10 centimeters. So that's the answer, negative 10 centimeters to the right of the mirror. And now I'll draw two rays. You know, the easiest rays are probably this one, parallel to the axis, and then that goes through the focal point, but you know, through the focal point, as if I were drawing it as if it was through the focal point, so that if I trace it back, it goes through the focal point. This is a diverging lens, so I know that the ray goes in that direction. The other one, probably the easiest, again, you only have to do two. Yeah, probably the easiest is just to go to the center of the lens. And it goes through undeflected, so I can imagine tracing it back. And then the image will be right here. That is a virtual upright smaller image. Okay, there's one other ray that you could have drawn. Um, this one's a little more difficult, but I can draw a ray that goes through the focal point. That is, it will go up to this point, and then if I trace it forward, it goes through the focal point, and then it goes parallel to the axis. And if I trace that back, it will also cross there. But most of you probably chose those first two. I hope that you did. Those are just a little easier. Okay. All right. Light behaves as a wave and particle. It lights as a wave. That would be these two. Organizing these in terms of increasing wavelength. Well, I know this has the shortest. So let's just go down and see. Oh, look, yeah, so it has to be this. And is this in the right order? Yes, shortest, next to shortest, and then long wavelength there. All right, let's do this mirror. So this is 40, that means this is 50. 50 plus 110, that's 160. So that means 180 minus 160 equals 20. This has to be 70. And so this reflected ray is also 70. So the index of refraction for medium 2 is less than the index. Let's just say N2 is equal to 1 and this N1 is equal to 1.5. Just sort of put some numbers on it. That means that this is slow, this is fast. Let's draw our wave fronts. If it goes faster here, it's going to move in that direction, so it's going to bend away from normal. Alright, so I have it moving from air, that's n equal 1, to this n. I know I can get rid of this one, by the way, because the n doesn't go less than 1. So I have 1 sine of 50 equals n sine of 30. And if I solve that, n is equal to sine of 50 over the sine of 30. Be careful when you're putting your calculator that it's doing the sine of 50 over 30, that it's the sine of 50 divided by the sine of 30. I get 1.53. So D is the right answer. Notice there are no units on index of refraction. It's a ratio of two values, two speeds, in fact. Here I want to know what angle must it go through in order to undergo total internal reflection. And you know, that's where this angle is equal to 90 degrees. But if you're looking at this, you realize that, oh, it's going to slow down here and speed up here. So actually, this is going to bend towards the normal. In fact, I can't get total internal reflection as I move from a low to a high index. So E is the right answer. If you tried putting this in your calculator, 1.3 sine theta 1 equals 1.4 sine of 90. If you tried that, you would have gotten an error in your calculator, and that's why it's just physically impossible. Oh, and then, so a similar question, what must it be doing? It must be traveling from an index of a high index to a low index. It seems to be this answer, but let's look at these others. Uh, no, this isn't true. It would be faster. And that's not true. It would be lower, which is A. And that's not true. If they have the same, it's just going to go straight through. And um, yeah, sort of, but not necessarily. It's not necessarily a single wavelength. I mean, you can put white light into medium, and it can have total internal reflection for all of the wavelengths. So most fiber optic cables operate, I guess, at a single wavelength. I think they do because they use laser pulses usually as the wavelength in fiber optics. But you can get total internal reflection with multiple wavelengths. All right, what is the object distance for the second lens? We've already done one, something like this, but this is just asking an interim question. So 1 over 50 equals 1 over 100. I'm doing the 1 over F, 1 over, this is P1. Solve that. All right, so this distance to the image is 100 centimeters. So this distance, which is what I'm looking for, is plus 20. What type of aberration? The color should key you in here that light of different wavelengths, because of the wavelength dependence on the index of refraction, is will bend at different amounts. The human has a lens that can change its focal length while the image distance remains constant. So the eye, this distance is the image distance, and the focal length of the eye can change. When you're looking, when is the focal length of the eye's lens the largest? That's when you're looking at something that's really far away so that the light rays are parallel. When they're parallel, and then those rays will focus at the focal point. If an object is closer, an object is up close, then the focal points move in, so the light rays will still focus on the retina, but they follow a different path. So when you're looking at something far away, your lens is really thin, it has a long focal length, but when you're looking at something close, it has a short focal length. That's why you lose your near vision as you get older, because that lens just gets less flexible. Use the lens to make an image that's upright and smaller than the object. All right, so that's going to tell us right away that it's my object, it's my image, that I have a concave lens. And the concave lens has a focal length that is negative, and so it's going to be negative 30 over 2 or negative 15. The object is 30 centimeters away, and I want to know what is the magnification. So I have 1 over negative 15 equals 1 over 30 plus 1 over q. Uh, that's negative 2 over 30 minus 1 over 30 equals 1 over q. That's 3 over 30, so q is equal to negative 10. And then my magnification is negative q, which is negative negative 10, over p, which is 30, or positive 1/3. I could have gotten rid of several answers here. I could have gotten rid of that one uh, and that one here because I know that it's smaller. Right, same here, but and this one also because I know it's upright. So it has to be either B or C. I can also get rid of E because I've already said that there is an image, so I didn't lie to you about that. So key thing here is that focal length, recognizing it's a concave lens and that the focal length is negative. All right, object is 4 centimeters high and its image is 8 centimeters high. What type of lenses form this image? That is going to be a convex lens, and the object is inside the focal point. This is the object, this is the image, just like a magnifying glass. So it's a convex lens with the object inside the focal point. Convex mirror has a focal length of 30 centimeters. F is equal to negative 30 for convex mirror. P is equal to 60, and I want to know just what is the image distance. So 1 over negative 30 equals 1 over 60 plus 1 over q. That's negative 2 over 60 minus 1 over 60 equals 1 over q. It's 3 over 60, so q is equal to negative 20. That jives with what I think it should be, that my object will be over here, and then my image will be over here. I'm going to find out my magnification, just make sure it's right. That's going to be negative negative 20 over 60, which is positive 1/3, so it will be smaller, a smaller image. All right, you see an upright, smaller image of yourself. Oh, okay, so that's same mirror, right? This is a convex mirror. That means that the focal length, which is c over 2, is equal to negative 20 over 2, or negative 10 centimeters. This is c right here. P is equal to 5 centimeters. I want to know what is q. So it's 1 over negative 10 equals 1 over 5 plus 1 over q. That's over 10 minus 2 over 10 equals 1 over, oops, excuse me, 10, 1 over q. So q is equal to negative 10 over 3, which is negative 3.3. Infinity, we talked about that. What are these are the correct rules? Let's go back to this. So here, if I have a mirror that looks like this, the focal point's here. If the mirror gets flatter, the focal point moves out here. If it moves flatter, then the focal length goes to infinity. It's bigger and bigger as the mirror gets flatter and flatter. Which of these are correct rules for drawing rays? That's correct. Not correct. It should reflect back on itself. That's not right. It should be focal point. That's not right. It should be focal point right here. So it looks like that's the answer. Okay, we've seen this question before. So the object or the image is always exactly opposite. What kind of mirror produces this image? Nope, none. I mean, if it was like this, that would be convex. Or if it were like this, that would be concave. Or you could have it like this, that would also be, excuse me, or you could have it like this, that would also be concave. All right? Which is drawn incorrectly. Okay, that one looks right. That one looks right. And that one too. And they all cross here at the same point, so that should be a clue to you. And an object inside the focal point, what kind of image will the lens create? It's going to create an image that's bigger and upright and virtual. It's like a magnifying lens. All right, I think that's all.